Hello, this video is section 7.1 from the Larson book, Introduction to Hypothesis Testing. Now, we've studied one branch of inferential statistics, which is confidence intervals. This branch is where we're testing a claim about a population parameter and then saying if we think a population mean is greater than that number, less than that number, or not equal to that number. Versus, confidence intervals, where what we were trying to do is with a certain degree of confidence, we were trying to place the population mean within an interval of numbers. Here, we're just testing it against a numerical value. All right, so we'll see what that's all about coming up here. And now, hypotheses, they come in a pair of statements that works together. We have the null hypothesis, HO, H0, the HO. It's always a statement of equality. So the null hypothesis will always have either less than or equal, or greater than or equal to. Then it will pair up with an alternative hypothesis. And I wrote this as either HA or H1, depending on what textbook's being used for whatever course I'm teaching when you watch this video, because some authors use HA, some use H1, but either one is fine. In other words, they're both the same thing. And they're a statement of an inequality that is the complement of the HO, the null hypothesis. So for example, and you'll see we come down here, so you see the alternative will always have a symbol of greater than, not equal, or less than. So when doing a hypothesis testing for the mean, they'll always come in these three pairs. Now the mu is just the population parameter that needs to be there written as mu, and mu0 is going to be whatever the numerical value is we're testing against. And you'll see that when we look at some examples coming up. So like it could say for this one that the HO is mu is greater than or equal to 20, and then it would pair up with an alternative of mu being less than 20. So you see greater than or equal to pairs up with less than or equal to pairs up with greater than, and equal pairs up with not equal. All right. So you'll be able to refer to these as you need them. You don't have to memorize them or anything. Now, when we have a hypothesis problem, all they have to do is they have to give you enough information to determine either the null or the hypothesis, alternative hypothesis. You only need one of the two to get the symbol from the problem, because they're going to have something that they automatically pair up with. So if you know one of the two, you can get the other because of what it has to pair with. And that's what we call the claim. So the claim can turn out to be either the HO or the HA. It just depends on the wording of the problem and what type of symbol does it produce. If it produces an equal symbol, or less than or equal to, or greater than or equal to, that means the claim will be the HO. And if it's alternative, it'll be the HA, being less than, greater than, or not equal. Okay. Now here are some, I don't like to get too tricky on the wording here, but here are some phrases, common phrases, like is or of, things like that. That's pretty much represents equals. Is not, differs, things like that. That would be not equal. At least or not less than, that's greater than or equal to. So you got to realize at least is not the same thing as greater than, because at least means includes the value. Okay, fewer than, less than. Okay, I think that's pretty straightforward, that it would just be the less than symbol. no more than, or at most, will be less than or equal to. And then more than, greater than, above, it would be greater than. Well, all right, let's try out a couple of things here. Okay. We're just going to write the appropriate statement and then label what the claim is. Like I told you, the claim can be either the ho or the ha. Depends on what symbol it produces. All right, consumer analyst reports that the mean life of a certain type of battery is 74 months. All right, so we look at this. Is the key word here. Is means equal. Equal is always a ho. Always, because you remember, go back to those three things on the other page. And it's the claim, because that's the part it's giving us. And so as long as we know that equal has to pair up with not equal. And that's all I was mentioning here before these symbols, is that they only have to give the information for one of the two, because the other one will come just from how they have to pair up. So be equal pairs up with not equal. This one says a company claims that its brands of paint have a mean drying time of less than 45 minutes. All right. Less than. Okay, symbolically, that's pretty straightforward. Less than is less than. But the less than symbol right here must be the alternative, must be a ha. Because by definition, if it doesn't have equal, it's a ha. And then it pairs up automatically with greater than or equal to. Once again, everything back up with these. You know, you're always working off these. So you might want to just keep those written down handy as reference. So you don't have to be like going through the notes all the time to be looking for them. All right, let's see. Third one, you claim that the mean score for all NBA games for a particular season was more than 100 points per game. Okay. More than, that's your key phrase right here. More than means greater than, and it doesn't have an equal. So more than, greater than would have to be the alternative, the ha, and it automatically pairs up with a ho of less than or equal to. So here, if you look at these three, you can kind of see them all on the same page. The claim can be either the ho or the ha. It just depends on the symbol produced by the wording of what the claim is asking. If the claim is asking something that has equal in it, it's going to be the ho. If it doesn't have equal, it's going to be the ha. Types of errors, okay, and level of significance. Now, when we say errors here, we don't mean errors in a sense of a mistake that we make or we do something wrong. And let me give you an example. I didn't mention this in the confidence intervals stuff, but let's just say if you're doing, for example, if you're doing a 95% confidence interval and your population parameter, that means with 95% confidence it will be in your interval. Well, it also means there's a 5% chance that it's wrong. So that's what we mean by just an error in the process, not a human error. But anyway, here's what we do when we test the hypothesis, what we're looking for. We reach one of the following two conclusions. We either reject the null hypothesis, so we reject that ho, or we fail to reject the null hypothesis, so we don't reject that ho. Now we're going to talk more about this as we go. You might be wondering, does fail to reject the ho mean, is that the same thing as accepting the ho? No, it does not mean we love the ho. In statistical terms, failing to reject the ho strictly means that, okay, we may not agree with it, but we do not have the statistical evidence to say that it's wrong. It doesn't mean we agree with it, but we cannot significantly state that it's wrong based on our statistics. Okay. So it'll come up a little more here. And the two types of errors in the process that would maybe generate false results. A type 1 error. A type 1 error is if you reject the null hypothesis if in fact it turned out to be true. In other words, you rejected the hoe and the hoe was true. Well, that obviously would be a mistake to do that, wouldn't it? So that's what a type 1 error is. And a type 2 error is if we were failed to reject the null hypothesis if it's false, meaning it turned out that the hoe was wrong and we did not reject. So that's the two types of errors. And don't worry about this. I got this from another book. Don't worry about that beta. That's a Greek letter beta, by the way. But we'll be using this alpha. That's a Greek letter alpha. That's going to be a numerical value that's given to us in the problems. We don't need to worry about this beta. So what are they just saying here? We call that a type 1 error. It's called a false alarm. Don't worry about that. So type 2 error, they're saying missed opportunity to take some corrective action. Well, all right. Don't worry about that. But this little flow chart here sort of shows you. Now, these are not equally likely probabilities of all four of these happening. The probability of making this type 1 error is going to be actually low, a low number. So this is just kind of, if you read this where row meets column, if you do not reject the hoe and the hoe is true, that would be correct. Now, if you come down here, if you rejected the hoe and the hoe is true, that's the definition of the type 1 error. Now come over to the second column. Do not reject the hoe and the hoe was false. That is a type 2 error. Then if you rejected the hoe when the hoe was false, well, that would have been a correct thing to do, a correct decision. Now here's a phrase here called the level of significance. It's the maximum allowable probability of making a type 1 error. It's denoted by the Greek letter alpha. And I wouldn't worry about the part in red. I'm saying common ones are 0.01, 0.05, and 0.10. They seem to be the most used. But it can be anything, 0.04, 0.07. So when you see we start reading problems, it can either tell you, it can either say the level of significance is 0.05, or it can show this Greek letter alpha and just say, all right, alpha equals 0.05. So we just need to know that that's the same thing no matter how it's shown. Either way. All right. Okay, now this, here's an example of sort of the idea of type 1, type 2 error, and the idea I was talking about earlier about failing to reject the hoe does not mean you accept or embrace the hoe or agree with the hoe. So let's look at this example. Use this criminal justice system for example. Theoretically, the defendant, the null hypothesis, the defendant is innocent, and then the alternative is they're guilty. So a type 1 error is rejecting the hoe when the hoe is true. So in other words, in this case, it means an innocent person is found guilty. And of course, that's really, really, really bad. We certainly don't want that to happen as little as possible. I mean, the next one's not great either, but I think it's not as severe as the type 1 error. So a type 2 error, by definition, is you failed to reject the hoe when the hoe was false, meaning you didn't reject their innocence and find them guilty when in fact they really were guilty. So basically a guilty person was found not guilty. That's not good either, but certainly not as bad as convicting an innocent person. That's no good. Okay. So And another thing I'll mention on this problem too, if you think about any kind of, court procedural drama show or something like that, they, even though this, the null hypothesis is innocent and then the alternative is guilty, when they read a verdict, they never use the word innocent in a verdict. They use the word not guilty. So what that's saying is that that we don't, if we find them not guilty, maybe, we're not 100% sure that they're not guilty, but we don't have the evidence to reject the null hypothesis, meaning, so not, in other words, they never read, and most of the time those people are going to be innocent for the most part, but obviously, type 2 error means somebody could get away with it. So, yeah, you're not proudly proclaiming their innocence most of the time. You're just kind of saying, okay, not guilty, not enough evidence to find them guilty. So that's kind of the reason why you're not really accepting or supporting the Ho. And this kind of stuff, when we start using numbers and stuff, it's a very strong statistical statement. If you reject the Ho in favor of the alternative hypothesis, that does mean you strongly support the alternative. You strongly support it. But my point is, if you do not reject the Ho, that doesn't mean you're supporting the Ho. Yeah, this, unlike confidence intervals, this has a lot more sort of theoretical stuff to it, a lot more build up before we start actually working any real problems, which will be in the next section. A lot of terminology and stuff to kind of get a feel for here. All right. And these can be a little tricky, but you don't have to worry like, half your test isn't going to be these kind of questions or anything, but they can be a little tricky. You have to kind of think carefully on them. No math really involved here. So just telling us we have a null hypothesis where we're claiming the population mean is less than or equal to 47, which automatically makes the alternative mu is greater than 47, because they would work together that way. Less than or equal to would definitely pair up with greater than. Now, what result regarding, there's three things to this possible question. I took out that part D because whatever it was kind of ridiculous and irrelevant. But it's three things can happen if you go back up here and look at this. Yeah, it's either going to be correct thing to do, it's either going to be a type 1 error, or it's going to be a type 2 error. One of those three answers. I think whatever D was something that was tricky, and I wouldn't want somebody to even think that was the right answer, so I would not have that there. Okay, it says, we conclude that the mean is greater than 47. So you see, that's the alternative hypothesis. So if we concluded that the mean was greater than 47, that means we then rejected the Ho of less than or equal to 47 in support of greater than 47. That's what that means. Now it's telling us, so that's what we concluded based on our results. And then somehow, by some magical way, see, you're not really going to know this, that part, that's the whole, thing behind this. But let's just say it's hypothetically, what if the true value of the mean, population mean we learned somehow was actually 52? What happened here? Did we make a type 1 error? Did we make a type 2 error? Or did we make a correct decision? Well, if you rejected this Ho in favor of the mu being greater than 47, and it was really 52, that would have been the correct thing to do. That would have been correct, because the 52 was greater than the 47. So that would have been a correct decision. Now, I'll just verbalize for a second. What if we change this, everything but the last number here? What if we said the same thing? We rejected it. We supported the alternative, that the mean was greater than 47, when the mean was actually 42. Well, since 42 falls in the less than or equal to 47 range, so that means the Ho is true. So by definition, If you reject the hoe when the hoe is true, you have made a type 1 error. So basically what we're saying here for this, if that number is anything over 47, we made a correct decision. If it's anything less than or equal to 47, we would have made a type 1 error. I know, that can be a little confusing. All right, look at the next example. Okay, they give you the hoe and the ha here. Want to determine if the running time has increased. So they're trying to see if, if you've, in this case, increased would be greater than. So, rejecting the hoe in favor of the ha. So this says, suppose that we rejected we led to rejection. That means we, like the last problem, we support the alternative right here. We support greater than 9.1. But here it says, in fact, the mean running time has not increased. It didn't go up. It's still it's still less than or equal to 9.1. So we rejected the hoe when the hoe was actually true. And therefore, we made a type 1 error. Next one. All right, so we've got a SAT math scores. We're testing equal versus not equal, 500. Now this one says non-rejection of the null hypothesis. We didn't reject. All right. And then right here, if in fact the average SAT math scores has changed from the 1990 mean of 500. So what we're saying is that the alternative hypothesis is true. We did not reject the hoe. We did not reject the null hypothesis when in fact we should have rejected it. So it's already an error. We should have rejected it in favor of the alternative. So not rejecting the hoe when the hoe is false, by definition, means you've made a type 2 error. All right, so now, statistical test and p-value. So that's kind of what we're going to be getting into more in the next section. A test statistic, which you're going to see what that is, and like it says here, combined with the level of significance, when we start having numbers and things like that, where we're making our calculations, that's going to lead us to the conclusion, meaning in the sense of, are you going to reject that hoe, or are you going to fail to reject that hoe? And a value that we're going to also see from the calculations, it's called a p-value. I don't think you have to worry about the definition of this so much, but I have it here. It's kind of tricky to explain, but it's easy to work with as far as reaching your conclusion. So that's the good news. It's what to say here is the probability measure of how likely the sample results are going to be true. Okay. Now, the smaller the p-value implies that the sample results are less likely to be true. And it's also going to lead to rejecting the hoe. Now these three tests that were, these three hypothesis tests, these three pairs that were on the first page, they now each have names. So the one that's the greater than or equal to, that pairs up with the less than, that is called a left-tailed test. Greater than or equal to and less than. And what's going to happen, I'm just kind of showing you, is like on a normal curve, what's happening here is your test statistic is going to be a negative z. It's going to be on the negative side of the curve. And your p-value is going to be the area of the curve, normal curve, to the left of that number. All right. And the next one. The one that's less than or equal to with the ho and pairs up greater than for the ha is called a right tail test. It's going to have a positive test statistic over here on the right side, and then the p-value would be the area to the right of that test statistic. Now on a two-tailed test, equal not equal is one called two-tailed test, because it's two ends, because it's, you know, if you say something is not equal to something, it can be not equal by being smaller, or it can be not equal by being larger. You know, if you say, okay, mu is not equal to 10, well, you know, if it was 6 or 12, it's on, you know, either end, where the other ones are one direction, you know, less than or greater than only go one way. Now what happens here, the test statistic might be either negative or positive. So what happens is that you have half the p-value at each end, and then it'll be the two combined together to make the entire p-value. So the way you can do this, if it gives you the test statistic, is whether it's positive or negative, you can treat it as negative, and if you just get the p-value here on the left side using whatever technology, you get the p-value, and then just multiply that number by 2, and then that's going to do it. That'll get you the value you want. So the chart would work. I didn't do this one in the calculator. I guess I could. The Excel is actually a lot better, but if you use the norm S dist. So even though it's telling us that it's 2.34 for a two-tailed test, it automatically, whether it's positive or negative, covers both ends. That's only for two-tailed. So it's to the right of the positive, to the left of the negative. Now, I'll show you the normal CDF in the calculator if you really like using that. I'll go ahead and do it. Maybe I could squeeze it in here in the notes and leave it. How much room do I have? Probably be tough to make it fit in there, but might be able to. So, yeah. So it's 2 times norm S dist, negative 2.34, and that has to be true. For the normal distribution, which we've already studied, that was always a true. Now, binomial, sometimes it was true, sometimes it was false. True means cumulative. That means by saying true, it's going to give you all that area right there. And then multiplying it by 2 will give us the answer we need. But it's only for two-tailed tests that we do that. I guess I can put the calculator in here. If I go 2 times normal CDF, and we're coming from the negative, yeah, so there, okay, it's already there. That's already what I want right there. Negative 1e to the 99 for my negative infinity. That's what I want. I want negative 2.34 for the upper. There it is. Let me so I can get all, it'd be easier if, yeah, if we can all right, so I just copied the calculator screen part that didn't show the answer, because that way it'll be easier to see, you know, if you're looking at it yourself. So if I hit enter, yeah, I'm just not going to copy that part. Oh, I forgot to put the 2 in front of it. I'm sorry. I put the 2 in front of it the first time, and it came up to be the 0192. So that's the correct one, the top one. But it needs to have a 2 in front of it, or multiply it by 2 afterwards. Either way. Does it have to be in front? There you go. All right, so now a couple of examples. You're just reading the statement and setting it up like we did earlier, except now using the new definitions for left-tailed, right-tailed, two-tailed, we're going to identify which one it is. So, ILMA claims that the mean GPA for all UHD students is more than 2.9. Determine whether it's left-tailed, right-tailed, or two-tailed. So let's get the ho and the ha set up here. More than is greater than would be an alternative, the ha. And then by definition of how they have to set up, and it's the claim, it would pair up with a ho of less than or equal to. So it would pair up like this. Now if you get this part set up correctly, you should have no problem getting that, because all you have to do is just look at these definitions. Yeah, if you get the ho and the ha set up, you should never miss this if you get that right. And you see that's just called the right-tailed test. And what we got here, Lucy claims the mean GPA for all UHD students is 2.8. Determine left-tailed, right-tailed, or two-tailed. Is translates to equals. So equal, by definition, has to be a ho. So that's the claim. So the ho will be equal, mu equals 2.8. And then it also pairs up, the equal pairs up every time with not equal. And then go back and look at those. Equal, not equal is a two-tailed test. Okay, let's see. And okay, let me just kind of look through some of this. It's probably a good idea for you to read this. So yeah, so here is what I was talking about earlier. Failure to reject the null hypothesis is not proof that it's true. But if you reject, it's far more likely that the alternative is true. So therefore, if you fail to reject the null hypothesis, you can only conclude that there is insufficient evidence to warrant its rejection. So you just cannot, you may not agree with it per se, but you just cannot say it's wrong. So I'll look at some of the highlights here. So if you reject the null, you have statistical proof that the alternative hypothesis is correct. Okay. Statement of the null hypothesis always has an equal sign, whether it's equal, less than or equal to, or greater than or equal to. The alternative will not contain an equal sign, either less than, greater than, or not equal. And we'll see this come up in the beginning of the next section. But I believe I put it here also, because I think there's a question in the homework for this section that has it. So then we'll see it again in the next section anyway. So it's all right to go ahead and, so now we're getting our first taste of, the rejections and stuff. So using the p-value with the given level of significance alpha, if the p-value is less than or equal to alpha, then you reject that ho. Ho is gone. We reject the ho, we support the alternative. If the p-value is greater than alpha, then we fail to reject that ho. All right, so now suppose you conduct a hypothesis test that produces a p-value of 0.002 and the level of significance is 0.01. What's your conclusion? Is since 0.002 is less than 0.01, we would reject the null hypothesis. You always want to write the p-value first, and then on the right, you write the alpha, the level of significance, then you decide which way your arrow goes. And less than means reject. Now you got to be careful here because, yeah, 2 is bigger than 1, but that extra 0 in front of it actually makes it smaller. Now I'll show you a couple of ways that you could, if you needed, if you were struggling with this. If not, then don't worry about it. But one way is if you took this number and moved it 3 decimal places, and you'd have a 2. Here, you still move it, you got to move it the same on both sides, and you move it 1 more where there's nothing there, that actually adds a 0 there. So moving it 3 on that one gives you a 10. Now it's super easy to know that 2 is less than 10. So you can move the decimals the same number of places on both sides, and that will make the numbers, like whole numbers where they're easier to tell. That way you won't make the mistake of worrying about how many zeros are in front of it. So, all right, there we go. If that's giving you an issue. All right, so I think that's going to take care of the lecture portion of this. So now it's time for some homework. Oh. Bring this right back up. Alrighty. Okay, some of these conceptual questions, I'll leave those there. We define the type 1 error. Let's see. What are the 2 decisions? A lot of stuff here. Well, that's one of them. Reject. Yeah, these are the only 2. The rest of it's just a bunch of nonsense. Yeah. Sure to put a lot of nonsense questions in there. Let's see. All right, some of the stuff. Yeah, I'm sure most of these are going to be theoretical questions anyway, so I guess I should start looking at. Let's see. And hypothesis test, I didn't mention this in the lecture, but you're under the assumption that the null hypothesis is true. Yeah, that's but ideally though, if somebody setting up their own statistical test, if they think that the alternative, if they'll set it up as if they think the alternative is going to be the result they're looking for, you want to reject that null in favor of the alternative. So even though that's the assumption when you set it up, although we don't if we don't reject it though, that doesn't mean we support it either though. So, but ideally, if you reject the null in favor of the alternative, that's means the alternative is likely true. That's going to be true. If you reject the null, then you can support the alternative hypothesis. Yes. All right, let's just keep hopping along here. This one, large p-value, will favor rejection of the null hypothesis. No, small p-value. Small p-value. P-value needs to be less than the level of significance. Tiny, tiny p-values are what's going to be leading us to rejection. All right, this is kind of what I was just saying a couple of problems ago. You know, if you want to support the claim and you were doing this yourself, keep in mind you're just going to be answering problems as the wording is presented to you. But if you were trying to set up a thing, okay, I think that, you know, this is really going to be greater than, so I want to set this up as the alternative to be greater than, and then the hoe to be less than or equal to. So this is false. If you want to support a claim, you need it to be the alternative, because that means you're rejecting the hoe. In other words, if the claim is the hoe and you don't reject it, you're not supporting it. You can't ever support the hoe. You can only support the alternative. Okay, I think that one's easy enough. Let me see what's coming along here. Oh, don't worry, this is for standard deviation, which we're not going to be doing in this course, but it's the directions of the arrows. Like I said, I wonder when I picked this problem, maybe they had a mean symbol and maybe it scrambled it or whatever, but that's okay. That's still less than or equal to paired up with greater than, is you can go back to the same, even though it doesn't have the first symbol is not the same, it still meets this criteria right here. It's all about the directions of the arrows. So going back to this, that means with the greater than as your alternative, that is a right tail test. Let's see, how many of these are there? We see there's a lot of questions in this one, but I'm just going to look ahead. But a lot of them is not really that involved. I'll probably come back and do one of those. Oh, type 1, type 2, we'll look at that. I may not do both of them. Okay, here they're using P for proportions, but that's okay. Just don't worry about the symbol there. Or maybe I'll do that one and leave this one alone. Now, fire station publicizes that most 10% of its applicants become firefighters. At most means less than or equal to. So, bring up. All right. That's going to be 0.10. That's our hoe. And then, of course, that's also, let me write that was the claim. I'm doing this with a mouse pad. And then the ha is greater than or equal to, I'm not, it's greater than, excuse me. Forget what I just said. Greater than. Yeah, less than or equal to pairs up with greater than. Sort of misaimed a little bit there, didn't I? See if I can grab it and drag it down. All right. Now let's see what it's asking. Okay, type 1 error, by definition, means you're rejecting the hoe when the hoe is true. So now let's look at this. One thing, if you look right away, is that it's got to be either B or D, because look what it has listed for the hose. A has greater than or equal to, C has greater than or equal to. But at most definitely means less than or equal to, so that narrows it down right there. And so you reject the hoe when it was true, meaning that it really was less than 10%, but you rejected that. And that looks like D. So it was true, meaning at most 10% was true, but you rejected that 10% was true. Fantastic. Oh, this one's got type 1 and a type 2. Okay, that's good. Type 2, failing to reject the hoe when the hoe is false. Now this one answers A and B. Automatically they have the wrong hose. Greater than or equal to, so it's got to be C or D. And type 2 error is failing to reject the hoe when a hoe is false, meaning it turns out that it is greater than 10% is correct, but you did not reject the hoe and say that. So let's look, I think it's this one. It's more than 10%, meaning the alternative was true, but we did not reject the hoe that it was less than or equal to. So I do believe that's got to be our answer. Excellent. So I'll leave the other one. What was 15 again? Is that worth? I could look at that one. Let's do one more. Let's see. Oh, these aren't too bad, I don't think. Like this one, for example, says at most 20,000 people. So you would want this. And now it's probably going to, yeah, here we go, asking for the pair. So that less than or equal to 20,000, that's got to be a hoe, and it's got to pair up with an alternative of greater than 20,000. So I like that answer. So they've got to go in the right position. But look at answers C and F. You know, that's why it's important, because you see it's got the less than or equal to and the greater than, but they're in the wrong positions. A hoe cannot be greater than. So they're claiming at most is 20,000 people. So the less than or equal to 20,000, that was the claim. That's the claim in the problem, which happens to be the hoe. So, right there. The null hypothesis less than or equal to 20,000 would be the claim. All right. And then we'll take a look at 15. That'll be it. All right, let's see. Yada, yada, yada. Scientists claims that incubation period for eggs of species of bird is less than 32 days. Is it a null or alternative? Okay, less than. Okay, we know what less than means. No equals. Less than is no equals. So does not contain a statement of equality. Therefore, that means it represents the alternative hypothesis. How should you interpret the decision that rejects a null hypothesis? So we're saying we reject. We support the claim of less than 32 days. So we say there is sufficient evidence to, because the claim is alternative, we support it because we're rejecting the null, meaning the claim is the alternative, so we support the alternative. And so there's sufficient evidence to support that claim. All right. Oh, there we go. More. Fails to reject. There is insufficient evidence to support again. So we don't support insufficient evidence to support the claim. I guess that one ended. Oh, it was the last question. That's why I didn't go forward. So, well, all right. I think that's going to conclude this video on intro to hypothesis testing.